Well, hello there, boys and girls and friends and neighbors. Today we are going to talk about the MM1 finite capacity queue, so where we have one server, and then I'm going to talk about the MM and then multiple server finite capacity queue, and then we'll do a few queuing examples just to kind of exercise or flex our new queuing muscles. All right. So the first, the next slide actually, is the MM1 finite capacity queue, and I'm just going to draw the state transition diagram for this. It's pretty darn simple. We're going to have a system capacity, and I apologize for the shadows here. I am actually out of town working at my sister's house, and it's a cloudy day, so I don't have some great lighting as usual. So the system capacity, meaning, when I say system, I mean everybody in the queue and then the one person in service. So the system capacity is going to be represented by this capital letter K, all right? So we could have no one in the system, which means my one server is going to be idle. We could have one person in the system, which means my server is going to be busy, nobody in the queue. We could have two people in the system, which means we have one person in service and one person in queue, and then so on. And we could keep on going here up until my system capacity, which would be K, meaning that we would have K people in the system, we would have one person in service, and then K minus one people that are in the queue. My server is just, since I only have one server, they will be working at a service rate of mu, and we're going to assume a constant arrival rate here that is not state dependent. So we'll have an arrival rate of lambda going from 0 to 1, from 1 to 2, from 2 to 3, and so on, and you get the idea here. And then I'll have a service rate, which will be a constant at mu here, so 3 to 2, and 2 to 1, and 1 to 0. So that's what the queue would look like, so there's really no surprises there. Now the values, if you were to set up these balance equations, you can solve for some closed form expressions for the steady state probabilities and also for the parameters of interest. Sorry for this little, doesn't look very good there. So we can easily solve for my probability of being in whatever state n, which is the number of people in the system. And just a gentle reminder here that we have this rho. Again, I'm a terrible Greek letter drawer. Rho is going to be my arrival rate over my number of servers times my service rate. So in this case, because s is equal to 1, right here we know that this is 1, rho is just going to be lambda over mu. And then by using that rho, we can, makes for a nice little expression here. So my steady state probabilities, P sub n, will be rho to the power n, 1 minus rho. And then the denominator will be 1 minus rho to the k plus 1. And this is good for the number of people in the system of 0 or 1 or 2, all the way up to that letter k. And then these are well, this is a nasty equation here, and it's really, really easy if you're trying to figure out the number of people in the system right here, which is L, the average number of people in the system. Super easy to make a typo when you're doing this equation. So don't expect to see this on quizzes or exams, but here's the actual values. And again, I recommend that you go to that website. Website. It's I mentioned it in the last video. I told you to bookmark it because this will actually crunch these numbers for you. Obviously, you're not going to use that on an exam or a quiz. However, you might actually need it though for some other course or maybe for some analysis that you're actually doing. So you're going to definitely want to use that site to help you out. So this is the equation for the number of people in the system, and then the last term down here is that. So you might want to pause the video here and write that down. And then the number of people in the queue, that's just going to be the number of people in the system. These are average values. I keep forgetting to say average. Average number of people in the system minus, and then we'll have 1 minus the probability that the server is idle. Then we can have the average amount of time spent in the system, which will be the average number of people in the system divided by my arrival rate. And then we can also have the average amount of time spent in the queue, which will be the number of people in the queue divided by the arrival rate. So those are the equations that you'll want. And again, you're really going to want to use that website. So here is a nice little example here, and has to do with a gas station, basically, here, right there. So we've got a single server here, and it says that at this particular gas station, there's room for 1 car being served and for 2 to wait. So in this case, my system capacity is 3. At most, I can have 3 people in this system. So we want to set up the state transition diagram, the steady state probability equations, and then what we want to do is, I'm going to change this third one. Instead of the expected waiting time in the system, I just want to change this, just to change it up a little bit. What is the probability that the system is full? So that's what I want to write. What is the, I'll write it here, probability that this system, I'll say that the system is at capacity. Let's put it that way. What is the probability the system is at capacity? That means that, you know, we've got as many cars being served, which is 1, and 2 cars waiting. A, set up the state transition diagram. So if I take a look here at the wording, it says cars arrive at a service station at a mean rate of 15 per hour. So they just gave me what lambda is. So we have 15 cars per hour arriving at the service station, and it says that we have one service position with a mean servicing rate of 27 cars per hour. So they gave us directly lambda and mu in this problem, cars per hour. So setting up this state diagram is going to be really quite easy. We have a maximum number of 3 cars that can be in the system. We know that the arrival rate up here is going to be 15. I'll just write 15 here, 15 cars per hour. We know what it is. And then the service rate is going to be 27 cars per hour. Know that I care about units though, so on an exam or a quiz, I'm very likely to ask you to note the units here, which means I probably should. I'll just write per hour. I know me. It's an itch that I can't scratch. There we go. There, I scratched it. We're good. So that's my state transition diagram. Part B says set up the steady state probabilities, and that's pretty easy to do. We know that the expected rate into a state has to equal the expected rate out. So for state 0, we have, I'm going to write it this way. We have state 0, we have state 1, we have state 2, and we have state 3. So the rate into state 0 is going to be, expected rate in will be 27 times the probability that I'm in state 1, and that has to equal the rate out, which is 15 P0. And then for state 1, we would have the rate in would be 27 P2 plus 15 P0. And that has to equal the rate out, so that's going to be 42 P1. And then for state 2, we would have 27 P3 plus 15 P1. Is that right? Yeah, sometimes I mess that up. And that would be 42 P2. And then finally we would have 15. Wait, it's the rate, let me be consistent here. The rate into state 3 is 15 P2, and the rate out of state 3 is 27 P3. And of course we know, I'm just going to write, this isn't a steady, this isn't a balanced equation, but we know that if we, that these are not linearly independent. So if we wanted to solve for these, and it is pretty easy to solve for them, by the way, we know that we have to add up additionally that all of those probabilities have to equal 1. And in fact, for part C, that's what we are gonna have to do. And so if we wanted to, you could certainly solve them this way, or you could just use the equation that is on the previous page. I think I'm just going to use the equation that I gave you before. So we know that rho is equal to lambda over mu, which is 15 over 27, and I think I'll just leave it that way. And what it's asking for is the system at capacity, so they want me to find P3. And from the previous page, we know that that's going to be, I'll just write it, let's see, that will be rho to the n, so in this case, 3 is n. So it'll be rho to the third, 1 minus rho, and then over 1 plus rho to the k plus 1, which is, again, k is 3 plus 1. And when you plug all of this in, let's see if I plugged that on all correctly. I believe that I did. You should get 0.0842. So the probability that if I go by this gas station and I just can't get gas there, it's too busy, or it's completely a capacity, it's about an 8% chance that would happen. All right. Now, how do we handle an MMS, finite capacity queue? So here we have one server. Now we're going to have multiple servers. And first thing we'll do is we'll draw the state transition diagram for that. But the next slide is, there's no equations in the textbook for this particular system. And that's because it's dependent. The equations, there's no closed form because it depends on the number of servers that we actually have. But what we can do is we can certainly draw the state transition diagram for whatever situation we've got. So here's an example. We've got 2 repairmen. So in this case, oh crap, you know what I forgot to do? I didn't change it to the author's notation. I'm just catching this. Hang on a second. Go back. So sorry. Right, go all the way back here. That's fine. That's good. That's fine. Here's where I screwed up. The authors don't use that S. I mentioned this in a previous lecture. They actually use a little m here. So that's my fault. I don't like the little m because there's too many m's, but let's just fix this, okay? So here we've got an MM, and just where we see that little S, make a little M, okay? Okay, now I feel better. We got these 2 repairmen. So here we've got M equals 2 servers. They're fixing these soldering machines, and they at an exponential rate of 3 per week. So they just directly gave me that lambda, or I'm sorry, that mu, because they're fixing it at a particular rate. They gave me directly that they can do 3 fixes per week. That's always nice. Soldering machines break down exponentially. Oh, they gave me that too. They told me that my arrival rate, and arrival in this case is the arrival to the service people, right? So this is going to be 5 per week. And there's only room for 3 machines in the shop at a time. Okay, so it says show the state transition diagram and find the steady state probabilities. So if there's, again, this is going to be a capacity for 3. So we have K is equal to 3 in this case. So my finite capacity is that. But this time we have 2 servers. So I just used a small example, because if you get the small example, then you can certainly extend it to a larger example. So here are my 4 states that I can have. I know that I'm going to have breakdowns right here at a rate of 5 per week here. So again, these are not state dependent. They can be state dependent, but in this case they're not. They didn't indicate that they were. And then I've got 2 servers. So if I have 2 servers right here, here are my 2 servers, and I have 3 people in the system, that means there's a machine at server 1, there's a machine at server 2, and there's a machine waiting in queue, right? So what is the rate at which I'm going from 3 down to 2 that is going to be 2 times mu. So I have 2 servers working at a rate of 3 per week. So I'm going to have 2 mu, and that's going to equal 6 per week. And same thing, if I just have two working, nobody in queue, my rate at which I go from state 2 to state 1 is going to be 2 times my service rate, so that's going to be 6 per week again. And then if I only have one of these servers busy and the other one idle, then my rate at which I go from state 1 to state 0 is just going to be 1 mu, which will be the 3 per week. So that's my state transition diagram right there. Then what I'm going to do is I want to solve for the steady state probabilities, and I'm going to use my matrix function in my calculator because it'll work out quite nicely. But let me write the balance equations, and then I'll put those into my calculator and solve for those. Remind you how to do that. It's really very convenient if you can figure out how to do it in your calculator. So for state 0, if I set this up, I'm going to have 3 P1 equals 5 P0. And then for state 2, we'll have 6 P2 plus 5 P0 equals 8 P1. Something you might want to do, if you're not familiar, if you've never done this before, is pause the tape right now, or call it tape, but pause the video right now. Do these yourself and see if they match what I actually write down. You know, assuming I did it right. For state 2, we would have 6 P3. Remember, the rate into state 2 here will be 6 P3 plus 5 P1 equals the rate out. Only this time it's going to be 6 plus 5, so that'll be 11 P2. And then our last state, the rate into state 3, will be rate into state 3. I always do this backwards when I do it. The rate into state 3 will be 5 P2 equals the rate out, which is 6 P3. And then these are not linearly independent, so we know that the sum of all of those steady state probabilities will have to be equal to 1. And now what I want to do is put this into a matrix form into my calculator. And so if I were to set this up, P1, P2, P3, and then this right hand side, I'm going to set up a matrix in my calculator that is going to have it'll have 1, 2, 3, it'll have 4 rows and 5 columns. So I have 1, 2, 3, 4 rows, 5 columns. And if I put all of this so that the right hand side is always a constant, I'm going to end up with the following coefficients in my matrix. I'll have minus 5, and then a 3, and then 3 zeros. This is how I used to like to do it when I was an undergrad, put a double line there. And then state 1, we would have a 5, and then minus 8, and then a 6, and then 2 more zeros. And then for and then what I decided to do was I decided to leave out this equation for state 2. Remember, we have to delete one of these, so we have to omit 1. So I'm going to omit this one right here. And then my next equation that I'm going to use is for state 3. And so that will be 0, 0, and then we have a 5, where am I here, P2 and P3. What have I done here? Something different. 0, 0, P2 is a 5, P3 would be minus 6 and 0, and then this bottom one, did I do this right? Yes, I did. And this would be all ones in the bottom row. So what I'm going to suggest that you do now is to use this function in your calculator. And I see that I actually set up my equations different. I've done this ahead of time, but I'm going to have to edit one of my rows. But if you go to this matrix function right here, so I'll turn the thing on, and then we go second function matrix, And then what you can input your matrix here. I already input it as a 4 by 5 right here, but I'm going to edit it because I actually changed one of the rows a little bit. So you can see that in my calculator, I've got it goes 5, 5, 0, 1, 3 minus 8, 0, 1, 0, 6 minus 5. Oh, and here's where it's different, because I set up my last equation. When I put it in my calculator, I actually had 6p3 equals 5p2, and so I just did that a little bit differently. So I'm just going to edit my matrix here to reflect what I put in the lecture here. So if I go down here over, and I'm just going to edit this input. So instead of a minus 5 there, I have a 5. And then instead of a 6 here, I actually had a minus 6. It's going to solve for the same thing. I just have a switcheroo on the signs here. So enter. And then to solve for these, and you can see that my, hang on a second here. And the right hand side is 0, 0, 0, 1. So to solve this matrix, it does that, row echelon reduction here. I'm going to go to, again, second function. And then I'm going to go to matrix and math, and then I'm going to scroll down, or up in this case, to ref right there. Then I have to, oh, wait a minute, hang on, I gotta go fresh, hang on, I gotta go fresh. Come on, quick, baby. There we go. So I go second function matrix, then I go to math, and then I go, as I said, up to this R reference here. Then I'm going to input the matrix that I want it to solve for. So I do second function matrix again, and then I just have to hit enter here because I want it to do matrix A. I don't have to close the parentheses. In fact, in this calculator, when I do, it gives me an error. So if I just hit enter, it will solve for all of my probabilities. And I know there's a big glare right there. I didn't catch that, but these are what the probabilities are. So it's already solved for those. It's P0 is going to be 0.1918. P1, so it does it in order like this, will be 0.3197. P2 is going to be 0.2664. And then finally P3, which is what I want, is going to be 0.2220. So the question was to find the steady state probabilities, and if I was curious, when I said what I want, what I'm just curious about is what's the probability that this system is completely full, is going to be 0.2222. What if I asked you this question? What if I said, here's a little bonus question, what is the probability that both repairmen are busy? Well, what would the answer to that be? Well, the answer to that would just be they would both be busy if we have state 2 and state 3. So that would just be P2 plus P3 equals, whatever. You could add that up. But that's one way of asking a question that's a little bit different than just saying solve for the steady state probabilities. And this is that's something you might be interested in. If you're overworking your repairmen. So in this case, they're not, let's see, what is it, about 49% of the time they're busy. Maybe that means that they could be doing something else, whatever. Okay, so here's a few queuing computation examples. And I'm really just going to give you the answers when I go through these because I'd like you to actually solve them. So here we have some queuing computation examples. Not quite on the, there we go. So the first one, we have a one-man barber shop. So we already know that the little m here is going to be one server. But the question is it finite capacity or infinite capacity? So it's got 10 seats, including the barber chair. All right, so inter-arrival times are exponentially distributed with a mean of 15 minutes. Service times are exponentially distributed with a mean of 12 minutes. So what have they just given us? They just gave us 1 over lambda and 1 over mu. So you have to determine what lambda and mu are there. So be careful with that. first question is, what queuing discipline is this? And I think it's pretty easy to see that we're never going to do anything that isn't m/m, by the way. So it's always going to be mm, but we have one server here, but we only have 10 seats. So here we have a finite, you can say finite queue or finite capacity. It doesn't really matter. It says, what fraction of the time is the barber busy cutting hair? So if he's idle at P with a probability of P0, the fraction of the time that the barber is busy is going to be 1 minus P0. And if you do this right, you should get the following value, 7812. So all I'm going to do is give the answers here for these two problems. I'd like you to verify that you got the answers. If you don't get the same answers, then contact me or go on Piazza and ask a peer. On average, how many people will be waiting for a haircut? And here, like I said, just for this one, just use that website that I suggested so you don't make any mistakes. All right. Mostly what I want you to know from this is what is lambda and mu, right? So on average, how many people will be waiting for a haircut? Well, what they just asked me for was the average queue length, and if you run that, you should get a 2 point, and I'll take it out to 4 decimal places, 1851, and that would be what would you call them, customers, whatever. I like the units there. And D, what is the average amount of time that a customer will have to wait before he begins to get his haircut? And again, just use that website just to make sure, just let it do some crunches for you. I'm not going to ask you to use the website on an exam or a quiz, but just use it. I'd like you to get to know that it's out there. And so the waiting time in the queue is going to be 0.559495 for what? Depends on how you identified what mu was, and I want you to figure that out, and what lambda is. So if you did it in terms of hours, that's what the waiting time would be in hours, and if you did it in minutes, it would be it's approximately 34 minutes, which is about kind of right if you go to like a Supercuts or something like that. Next problem, and there's just 2 that I'm doing here. The next one says we have a muffler shop with 3 machines. Each mechanic takes an average of 45 minutes to service a car. Customers arrive at a rate of 1 per hour, and it says both of these inter-arrival times and service times are exponentially distributed. So from this problem, again, I want you to determine what is lambda and what is mu, but I'll give you the answers to these questions. This queuing discipline happens to be an M3 system. It looks like, because it doesn't say that it's limited, whenever it doesn't say that there's a limited number of, customers or cars or queue, then you're going to assume that it is infinite. So we have an infinite capacity queue here. So part B says, what fraction of the time are all of the servers idle in this case? So they're asking for P0, and that, if you run those numbers, will be 0.4706, and it says, how long on average does an incoming customer have to wait for service? So you have equations for this, right? And for C, again, you could probably use the just go ahead and use the website for that. So on how long on average does an incoming customer have to wait for service? So that would be WQ. And if you run that, it depends on how you express lambda and mu, but here's a couple of different ways. 0.147 hours, which is equal to approximately 53 seconds. That's a pretty short wait time. I'd like to go to that mechanic, right? All right, so run these numbers, see how it goes for you. These are sections that we're not covering. I'm only using chapter 4 to give you enough information so that we can get into chapter 5. And again, I'll reiterate, some of you have had IEE 470, so you probably already know some of what I've done. If you haven't had IEE 470, then it's still not a problem. I've just covered what I needed to here. I pretty much taught it as if I was teaching the beginning of IEE 470. And if you're in IEE 470, it's possible that you're getting this material in this course kind of in parallel with that course. I'm not exactly sure when the queuing actually comes up, but we will not be covering anything about MG1 queuing systems. I'm just not going to cover all of these remaining sections in Chapter 4. All right, next time we meet, we will be doing the beginning of Chapter 5. Have a great day.